discussing the tennis match Markov process, and I want to finish that up and do a bunch of different things today. So let's not dally-dilly. All right. So what are the corresponding eigenvectors to these eigenvalues? That's plug and chug, right? You subtract 1 times the identity, and this turns into a minus 0.4. And so you can see minus 4, 2, then the eigenvector is going to be 1, 2. It's going to be orthogonal to that vector. And if I subtract 0.4 times the identity, I have 0.2, 0.2. So obviously a reasonable eigenvector would be 1, negative 1, or negative 1, 1. So these are, I'm putting these in the same order as I put the eigenvalues. So what does this tell me? This tells me that if I take the diagonal matrix consisting of the eigenvectors, and I take the change of basis matrix.
You mean the eigenvalues? You said eigenvalues.
Yeah, I meant eigenvalues, thank you. Don't ever do what I say, just do what I mean to say.
Okay.
Now I want the change of basis matrix given by the word I didn't say.
Eigenvalues.
Right, eigenvectors. So I put in the first one in the first column and the second one in the second column, and we then know that A will be P lambda P inverse. And so remember what we were trying to do.
Just solve number 1.
Oh. What we were trying to do was find, given a certain initial probability vector, which we didn't specify, find what xk is for all k. So we're trying to predict the future, how these tennis matches are going to go. And so we said last time that a to the k is going to be p lambda to the k, p inverse. And I want to now point out to you how this has a really nice formula. So you start with the initial vector, your initial condition. You apply a once, you get x1. You apply a again, you get x2. You apply a again, you get x3. So you're getting the powers of a times your initial vector. Now let's write out what that looks like. That's p, which has in it the eigenvectors as the columns. So this is v1, the first eigenvector. This is v2. What does lambda to the k look like? Well, in our case, it's going to have these numbers, but I'm going to write it down in general just for a second, and then I'll put it in this specific case. We're going to take the kth power of the eigenvalues, and then we're going to have p inverse times the initial vector. Agreed? So what do you see happens here? This is some vector of constants. Right? You take whatever numbers are in your initial vector, you multiply that vector of numbers by p inverse, you get a vector of numbers. So these constants are determined by your initial condition and the p inverse metrics, but they're constants. What does this look like when I multiply it out? Well, I'm going to get, when I multiply this diagonal matrix times this vector of constants, I'm going to get C1 times the first eigenvalue to the k, and I'm going to get C2 times the second eigenvalue to the k. Now, recall from week 3 of the fall, or maybe it was week 2 of the fall, multiply a matrix, think of it in terms of columns, times a vector. What does that give you?
A linear combination.
Linear combination of the columns with those coefficients. So this is awesomely cool, because what are you getting? You're getting the first eigenvector multiplied by the first eigenvalue to the kth with an appropriate constant, plus second eigenvector correspondingly multiplied by some constant times second eigenvalue to the k. So this, what this is saying is that basically up to knowing the initial condition, which tells you these constants, your solution is a combination of these fundamental building blocks here. Lambda to the k times eigenvector. Lambda to the k times eigenvector. Those of you who have taken some differential equations or physics and have heard the expression normal modes, this is analogous to that. I'm going to show you that coming up later today. So in general, for any problem, you see that you can write down the exact solution in terms of knowing eigenvalues and eigenvectors, and then of course you need the constants. So in our example, lambda 1 is 1, and lambda 2 is 0.4, so we're getting xk is the first constant times 1 times v1 plus the second constant times the kth power of 0.4 times the second eigenvector. So the particular value of xk is going to depend on my constants here. But what happens if we take k and let it go to infinity?
Second term vanishes.
Because the eigenvalue has absolute value less than 1, in the limit it goes to 0, and 1 to any power just stays there, so you've got steady state. xk approaches what I'll write for now as x infinity, which I'm going to think of as the steady state solution. What is now? Does this remind you of a homework problem from last semester? I think Lana referred to this the other day.
Are we talking about that Wentworth problem?
Yeah.
Oh, yeah.
Oh yeah, it was xk over 5 plus
Iterating
xk.
a map and getting a fixed point. And
Yeah.
That's what this steady state solution is. It's a fixed point because it's an eigenvector with eigenvalue 1.
Yeah.
Right? So this is that same
So
phenomenon.
if it were less than 1, it vanishes. If it's bigger than 1, it blows up.
It blows
So
up.
if it's, only if it's 1, you get the
Right.
steady state.
But remember I gave you the exercise to think through. Because it was a Markov process, 1 had to be an eigenvalue, and in fact all the other eigenvalues, real or complex, have magnitude less than 1. That's a really cool theorem. If you're interested in the proof, I can give you one later. So fact for Markov processes, for any Markov process. You have one eigenvalue that's 1, and the remaining eigenvalues all have absolute value less than 1, including the complex ones. So you're always going to have a steady state solution. And in fact, lambda 1 equals 1 appears with multiplicity just 1. If you have a regular Markov process, something that isn't basically the identity. So there is a technical condition there, which I'm not giving you. Okay, so what happens? It doesn't depend, well, or does it depend? In the limit, what has to be the case here? These are all probability vectors. If you start with a vector where it represents probability of something and probability of not something, those add up to 1. And so because the columns add up to 1, if you multiply by a probability vector, you will always get a probability vector. All xk's are likewise probability vectors.
So the C1 doesn't really matter.
So what does that tell you? Well, it tells you that,
So it does matter.
well, hang on, you have to put in the P inverse here.
Okay.
So what happens if you put in, suppose you put in 1, 0, suppose we start off saying we know that for the first game, I've forgotten who it was,
Fred and Ricky.
Fred and Ricky. So if we know for the first game Fred is always going to win, then you have a 1, 0. What happens when you do the inverse times 1, 0? Where's P inverse? Well, I haven't figured out P inverse. What is P inverse going to be?
Third. 1/3.
Switch those two and negate those two. So notice C1 and C2 look like this in that starting case. Now if I did the other case, what would I get? I'd get 1/3 times the second column. What do you notice happens here?
That doesn't.
Those aren't changing.
Oh, and that's the only term that matters.
Yep. So I leave it to you to figure out why this has to be the case. But C1 is just going to be the number that makes this turn into a probability vector. So it has to be 1/3 to make the sum of this and this add up to 1.
Oh.
And no matter what your initial condition is going to be, that's always going to happen
So
here.
in your matrix for 2x2s, you have the first component of V1 is going to be the negative component of the first V2.
It's actually these two.
So basically, if we just said
Those
let
two.
x not equal alpha beta, then we've done the math, we would end up.
Yeah. So I'm going to let you guys, Cameron's thinking about it now. What is it about the Markov process that makes it be the case that C1 doesn't depend on the initial vector? So I'm going to let you think about that. So
So
exercise.
we could choose the eigenvector that makes it so that x0 or that c1 is 1.
No. Oh yeah. If you had chosen instead of 1, 2,
Yeah.
1/3, 2/3, C1 would have been 1. So this is exactly what Jackson just said. The C1 times V1 is going to make a probability vector. And so if you picked V1 to be a probability vector to start with, C1 would have been 1. So I'm going to leave it to you to figure that out. It shouldn't take you more than a few minutes. Okay, so there's a whole bunch of applications of this stuff in all sorts of different fields. Okay, I want to do 2 more applications today, so we got stuff.
So what was the final probably winning percentage?
Oh, I should have said that. What's the final vector? What's the eigenvector? We had 1, 2, right? So in the steady state is going to be that Fred wins 1/3 of the games and Ricky wins 2/3 of the games. Which isn't so surprising given that Ricky trounces Fred. And he doesn't lose very often, right? Relatively. So that's not so surprising. Is there another comment? Yeah?
Is there a way we can look at our original problem and like kind of figure out why that's the case or not? The only way we really do is Markov process.
I mean, from the numbers I gave you, how would you get that? I mean, you have to know about eigenvalues and eigenvectors. Well, you can find a way around it, but that's what's going on.
You can use those to write a formula.
Well, we have a formula.
Right.
Yeah. And I'm going to do that now for the Fibonacci sequence. So, we discussed the history of this a smidgen the other day. We're going to start off with a sequence that is given by this recursion formula. And you don't think about this is a linear algebra problem, but I will convince you in the next 1 minute that it's a linear algebra problem. And in fact, this is called a difference equation. It's an analog of what we're going to talk about next, which is differential equations, where you have a time that's discrete. Basically, you have integer indices for your sequence. A naught, of course. starts, and then you have A1, A2, A3, A4. So you can think about this as discrete time. Every day, you go to the next element in the sequence, and you want to know where am I on the kth day? So find AK. All right, how is this a linear algebra problem? Well, I seem to need two pieces of information to get the next piece of information.
So multiply a vector.
So I need a vector that stores 2 bits of information. I need a vector that stores where we are now and where we are next day. And then I can now get from xk to xk plus 1 by using this formula. So again, we have a transition matrix. Which says, how do you get from xk to xk plus 1?
That being that AK minus 1?
You just,
No. So I'm going to start with x naught, which will have a naught and a1 in it. And then I'll get from that to x1, which will have a1 and a2 in it, etc. Yeah,
Why did you use natural and 0 instead of just using whole numbers?
that's what that is.
Why would you just adjust? Is there not?
John, come on, leave me alone. So what is the matrix A?
okay. So
how do I get, I'm going to do it one step back. How do I get xk from xk minus 1? How do you get ak from these? So what do I
yeah,
put
you
here?
only, so 0, 1.
0, 1. How do I get ak plus 1? Well, I add those. There's the matrix. And as before, we want to start with an initial condition vector, which we have here, it's 1, 1. And we want to get the kth vector. So as before, x sub k is going to be the kth power of a times the initial vector. And as before, we're going to know how to write it in this way. I'm not going to go back through all the derivation of this. I'm just going to use the same general concept. This is going to be some constant, which we'll figure out, times the first eigenvalue of the matrix times the first eigenvector, plus some constant times the second eigenvalue, k times the second eigenvector. So let's find the eigenvalues and the eigenvectors. It will not surprise you to see what happens. What's the characteristic polynomial? Here's A, right? Let's not lose track of A. Here's A.
T squared minus t.
Determinant's -1, right? What are the roots of this?
The golden ratio.
So the roots are
1 plus or minus
1 plus or minus square root of b squared minus 4ac all over 2a.
So, square root of 5.
Mm-hmm. And so pretty much everybody in the room recognizes it with the plus sign as being the famous golden ratio. Okay, so we have lambda 1 is 1 plus the square root of 5 over 2, which is approximately what? And lambda 2, which is 1 minus the square root of 5 over 2, which is approximately what? Well, this is the product of their roots. So negative reciprocals. So notice this one's positive, this one has to be negative. Duh, of course it is. Well, square root of 5 is approximately 2.2. So this is approximately 1.6 1/8, I believe, is the next. And if you do 1 minus 2.2, that's approximately, so this is approximately negative 0.6. Notice that the sum of the two roots is the trace, which is 1, so these are supposed to add up to 1, and their product is supposed to be negative 1, which is sort of cool.
I got confused about that. Just pretty neat.
What's significant, as you shall see, is what happens to lambda 2 when you take it to the kth.
Oh,
Goes away.
it's left below ratio.
So what does this tell us? The leading behavior is that in the limit it's going to look like the ratio of consecutive terms is the Golden ratio. Alright, so let's, in fact, we're sort of done here, except I really should find the, I want a formula, so I want to find the eigenvectors. So if I take A minus lambda times the identity, I get minus lambda 1, 1, 1 minus lambda. But I know that the lambdas are chosen to make this matrix be singular, which means this row is a multiple of that row. So the eigenvector with eigenvalue lambda is what?
Just 1 lambda.
1 lambda. I mean, you can scale it, of course, but that's a basis for the eigenspace. For either lambda 1 or lambda 2. Okie dokie. So what would my P matrix be? It would be, well, let's put lambda 1 in the first slot, and lambda 2 in the second slot. It's a little yucky because I'm actually getting a negative here. So the determinant's going to be negative, but we can live with it. What's P inverse?
Lambda 2 minus 1.
Right, so lambda 2 minus lambda 1 I just said is negative, but it nevertheless is here. All right. And then I switch the diagonals and I negate the off diagonals and I get this. Now my initial vector, x naught, was 1, 1. So if I want to find my constants, I'm supposed to take P inverse times my initial vector, which is 1, 1. So what do I get when I do that? I get 1 over lambda 2 minus lambda 1, and then the sum. So I'm going to get lambda 2 minus 1, negative lambda 1 plus 1. So those are my constants. They look sort of wacky, but we can make life a little bit easier here.
Simplifying.
They have all kinds of crazy simplifying properties.
Well, what did we just say was true? We said, because the characteristic polynomial has these coefficients, we said the sum of the eigenvalues is 1, trace is 1, and the product is the determinant, which is negative 1. So,
Well, lambda 2 minus 1 is negative lambda 1.
that would be correct. So if I reversed those two, if I factor negative 1 out, then I would put a negative here, and I would have 1 minus lambda 2, and that's lambda 1. And I would have lambda 1 minus 1, and that would be negative lambda 2 here. Did I do that correctly? No, something's wrong.
Wouldn't lambda 2 minus 1
No,
be
something's
negative lambda
wrong.
1? Wouldn't the negative be on the top?
I factored out a negative from this.
Yeah, so
1
we want
minus lambda 2.
This is right. Now what about the second one? I want lambda 1 minus 1.
That would be negative
And I'm
lambda.
still getting negative lambda 2 here. Okay, I guess it's right. Okay, so where am I? So what does my xk look like?
Where did we get the vector to multiply p inverse what?
The initial condition vector.
Okay.
So xk is going to be c1. All right, so first of all, what is lambda 1 minus lambda 2? No,
No.
square root of 5.
Mm.
So we're going to get 1 over square root of 5. Very cool. And Haley can think about all sorts of things about what this has to do with what she's learning in her other math class. What do I have here? I have lambda 1 to the k. That sounds like lambda 1 to the k plus 1 to me. Times the first eigenvector plus, and then I have what here? Minus lambda 2 to the k plus 1 times the second eigenvector. What is miraculous about this is that the entries come out integers.
How we prove that?
Has to, right?
Why
You're multiplying an integer matrix times integer vectors. Has to be integers.
And it's like,
Yeah, so why is lambda 1 in particular? What is the k Fibonacci number? It is 1 over root 5 times the difference of the k plus first powers of the two lambdas. There's an exact formula for what the k Fibonacci number is. And you can prove easily by induction that this is always an integer, if you want to.
Why is lambda 1 to k plus 1 instead of k?
Why is what?
Lambda 1 to k plus 1.
Because we have kth power here,
Oh.
and then we had another coefficient here. So there's Fibonacci. And moreover, ak plus 1 over ak, the ratio of consecutive ones, we said in the limit, this goes to 0. So basically, a sub k for large k looks like this formula. Asymptotically, this is going to 0. So it looks like the k plus first power of lambda 1 over root 5. So if you take the ratio of two consecutive ones, of course, it just goes to lambda 1, which is the golden ratio.
another thing.
You call it phi.
Some people call it phi. We've had enough phis in this class that we don't need to have yet another one.
So let's go to the video just
So on web work and on your final exam, you will have some variant of this to do with some other equation like this, with some other initial conditions. Now, if someone's taking combinatorics here. Did you not learn a different way of doing that in combinatorics? With generating functions, finding the formulas?
Yeah,
It's
way
very
more-
similar to this.
much more painful.
No, it really isn't. It's actually,
Generating functions?
yeah, it's actually the same thing as what we're doing here.
So you could actually use this equation to find it for any sequence that's like this with any initial starting conditions.
Yes. Moreover, suppose you wanted instead of a second order recursion relation, suppose you wanted a third order.
Oh.
You'd have a 3 by 3 matrix and you'd do the same game.
So do we have that seeming that AK equals 1 times AK in the matrix is just so that way we get we can.
Sorry, I'm not following.
The reason why our matrix has to be 2 by 2 is so we have that AK equals 1 times.
No, the reason we were forced into by 2 was because we needed 2 inputs to get the next output. So you had to store both previous ones to get to the next one.
And the next one also needs to have.
Right, I mean, that continues.
Yeah, you want A to be squared too.
Yeah, you want a square matrix, obviously. Yeah.
Is there any like applications of the other ones that you were talking about? Like we did 3, like 8.
Now, I mean, difference equations come up modeling all sorts of things. I'm not prepared to do them off the top of my head, but any sort of discrete time modeling of physical systems, biological systems, and so forth can be put in this sort of thing if there's just one species. If you want to do more species, then you're talking about two sets of variables that may interact, and that's where I'm leading now with talking about differential equations. Any comments? So yeah, so this is a discrete time, and now what I want to do now is talk about what happens if you have continuously varying time rather than discretely varying time. And you might have, so the typical thing then, those of you who are going to those of you who have taken or are taking 2700, at the end they talk about 2x2 systems of differential equations. That's about what I'm about to do. And a typical application of that, and you'll do more of that in Math 4700, is modeling, for example, competing species. You have a fox population and you have a rabbit population, and the foxes eat the rabbits. They're not supposed to do that, but no one told them. And so the populations affect one another. If there aren't any rabbits for the foxes to eat, the foxes eventually die out. If the foxes eat too many of the rabbits die out. And so actually understanding this system is based on modeling it by a first-order differential equation, which is what we were about to
Doesn't
do.
that population like circle in if you graph it in a
Well, so take Math 4700 if you want to understand more generalized versions of this where they're not necessarily linear, but you understand the behavior by linearizing derivative of a map, and understanding from what we're doing today, you'll understand something about what the linear thing does.
I'm not like you ever do evaluations anymore.
Just Google it.
All right, so I want to talk about differential equations. So we'll do more on this on Monday, but I'm partly rushing because you have a web work problem on this, so I have to get to some of it. But we'll do more. We'll do more and do some really cool stuff on Monday with this. All right. So what we're interested in is a vector function of time. So in general, you would have a function from time to Rn, and you would assume it's a C1 function. So we can talk about differentiating it. This ought to be reminding you of something, and when I write down one more thing, you want to say, I know something about the derivative of that vector function with respect to time. It's given by some function of x, and maybe of time as well. So this is, in general, a differential equation that says how x changes depends on where I am and what time it is. This is a general sort of equation.
It reminds me of level sets.
What else does it remind you of?
Manifolds?
It reminds me of.
Where were you looking at? Where were you looking at a curve, g of t, that satisfied g prime of t was a vector at g of t? More recently, flow lines. You're finding a solution curve of a differential equation. So example was x prime of t equals a vector field at the point x of t. This is called autonomous because it doesn't depend on time. In general, you need a function here from Rn and time back to Rn. That's a time-valued vector field. It's a vector field that's dependent on time. So you did the simple case, you thought about a simple case in homework, and the qualitative behavior of these things is a fascinating thing to study. That thing I gave you in homework to show that if you had a closed line, the divergence of f had to vanish somewhere is the first baby step of interesting theorems to analyze these differential equations. All right, so the simplest case we're going to do is where this function doesn't depend on t, and it's linear. Where A is an n by n matrix. So just the simplest possible case is linear function of x. Well, I suppose you could tell me even simpler would be just a constant vector here. But that's too simple. I wouldn't even deign to insult your intelligence talking about that. So the question is, how do we solve an equation like this? And to be more like a physicist, the book uses physicist notation, and I believe WebWork has it as well, using a dot to denote time derivative. I don't know why the physicists do this. Do you know? No. So dot denotes time derivative. So you can put a prime, you can put a dot, it's all the same thing.
But you don't write the of t then? Like with the dot on the top?
You can, yeah. I mean, I'm going to get lazy and leave off the FTs mostly, but. So, in a 1-by-1 case, do you guys know how to solve something that looks like x prime of t equals constant times x of t?
Yeah.
Anybody else know?
Yeah.
Yeah, what kind of solutions do you have if a is constant? What are the solutions?
Involving logs.
Exponentials,
Oh, exponentials.
right? X of t is initial condition times e to the at. Those are the solutions. You can solve it by separating variables, as Daniel said. Well, I'd like to do something analogous for systems of equations. Wouldn't it be nice if I had a system of equations where I had n variables and they all depend on one another in a linear way? What would be the nicest case if you understand how to do this?
If there was a diagonal matrix.
It'd be so nice if it were a diagonal matrix. If only, you can break into song anytime you want here, if only A were a diagonal matrix, we could solve this.
But how? And then
So we diagonalize it.
So this is called, in physics and engineering, they call this uncoupling. Because x1 doesn't depend on x2 or x3, it just depends on itself. If you have a diagonal matrix. And then you would just have xi given by some constant, ai, times itself, and you would have a solution in terms of exponentials for all of them. And you would get a vector function that looked like exponentials e to the a1t, e to the a2t, and so on, down to the e to the a-n-t, times your initial vector. So what do you say to yourself now? Self. Let's diagonalize.
do we know it's diagonalizable?
So if only all matrices were diagonalizable, so all I'm going to talk about today is pretending everybody is, if A is diagonalizable, we can then write A as P lambda P inverse, where again lambda is a bunch of constants on the diagonal, the eigenvalues. P is the matrix of eigenvectors. And what you would get is a solution like this, except, well, let's see, let's do it this way. So let's say, how would I diagonalize the equations? If I started off with ax equals x prime, what could I do to diagonalize? Well, this is of course saying P inverse A P is lambda, right? So what could I do here? Well, what if I had this equation? Well, let's do what I have here. I'm sorry, I'm being a little silly here. Put in this. Okay, so if A is diagonalizable, you can write A as P lambda P inverse. And now I'm going to say, If I change variables, I can multiply and get P inverse x prime equals lambda P inverse of x. So if I substitute P inverse x is y,
How did this
What did you
magical
just
change
do?
of variables happen?
Yeah, what did that?
I'm saying,
Multiply P inverse and the
call this a new variable. And then this becomes
Okay.
P inverse x prime, which is y prime.
Okay.
So letting y equal,
So letting y equal P inverse x,
okay.
we're now getting the differential equation that is diagonal. And we know how to solve this. Right? You can solve this. We just said what the solution is. You get that y is given by a combination of exponentials, which I'm conveniently writing in this matrix form as a square diagonal matrix with the eigenvalue exponentials on the diagonal, times my initial y naught vector. Right? The first y is initial condition times e to the lambda 1t. The second y is initial condition times e to the lambda 2t, etc. How do I get x back? Sounds good, doesn't it? Get x by taking p times y. If you go back to when we did the change of basis formula, that's the exact thing I was doing during the change of basis formula. Except we called it x prime, we didn't call it. Unfortunately, I can't use prime today. But,
We are using y.
so therefore, what's my solution? So our solution, x of t of the original problem, is x equals py. Agreed? Y was p inverse x, so x is p times y. So that is p times this diagonal matrix of exponentials times y, and what's y? Oh, it's p inverse x. So y naught is p inverse x naught. Does this look remotely familiar from what we've just been doing?
A little bit.
I've just, instead of having the powers of lambdas to the kth, I have exponentials of lambdas. We still have the p and p inverse just like we had before.
So does that mean it reduces just like reduces to some sum?
So you're going to get exactly just as we had before, we called this our vector of constants that are given by knowing the initial condition of the problem times, and these are exactly the normal modes that show up in physics. If you've ever seen systems of masses on springs, did they do that in beginning physics? Well, if you know this stuff, it's not annoying. So what does this come out? By exact analogy, you're getting c1 e to the lambda 1t times the first eigenvector plus c2 e to the lambda 2t times the second eigenvector.
By analogy.
Well, I've proved it to you. That's what this is. But it's exactly analogous to what we did before, except that instead of having powers of lambda, you now have exponentials. So when you go from discrete time to continuous time, powers are replaced by exponentials. Now, what I will do for you, oh, I still have time. Cool. what we will talk about on Monday, so you have homework problems on web work which are asking you to solve some differential equations. This is all you're going to do. I've given you diagonalizable matrices. On Monday, we're going to talk about what happens when it's not diagonalizable. And that's actually quite interesting. And that also will play a role in what goes on in Math 4700. But in fact, what's going on here is, for any matrix A, it's not just diagonal matrices where I just stuck in e to the constant times t on the diagonal. For any matrix A, square matrix, square matrix, square matrix. For any square matrix A, we can define e to the A. And that's going to be an n by n matrix, another n by n matrix. So if you take any n by n matrix, you can define its exponential.
Are we saying just take e to the
Matrix. E to the individual element.
No, you are not going to do any individual elements. If you had done that, you wouldn't have had zeros off the diagonal, you would have had ones. It's absolutely not
so
doing
you're saying
that.
that's gonna be e to the a.
This is going to be e to the ta when a is diagonal.
Okay.
So you got 3 minutes
when
to.
a is diagonal, e to the a is just e to the.
Right, so when a is diagonal, this definition I'm about to give you is going to give you what we were already doing, e to the diagonals. So you have 3 minutes to remember ancient history. How do you define e to the x for x a real number?
Ours is inverse of
Yeah, inverse of log.
Inverse of log, wise guys say.
Which is the
But
integral of 1
I'm voting with Daniel's answer. Recall there is a Taylor series which I don't want to use n for obvious reasons, so I will switch to k. That's the Taylor series of e to the x, built by asking yourself what polynomial degree k has the best is the best approximation to e to the x at 0, taking the limit. For what x's does this converge? Come on, all you AP guys needed to know how to do this last year.
-1 to 1.
No. Go back to Math 3100.
I'm in 3100 right now.
That's fine. Oh,
Yeah, you should have been doing this ages ago. Use ratio test, you see it converges for all x, and in fact it converges uniformly to e to the x on any closed interval in the real line. So any of you guys who are getting ready to take real analysis have this stuff to learn. But in fact, and we'll discuss this starting on Monday, this series makes sense. If you remember, we talked about how absolute convergence implies convergence. So that was beginning of chapter 6. For any x in the complex numbers, or any x in n by n matrices. You can put in a matrix and take the sum of its kth power over k factorial, and that will converge for every n by n matrix. And that be the definition of e to the a. So we will go on with this on Monday, and we're going to do some examples of non-diagonalizable things, and complex numbers will come back to visit us.
And so now